Hello, so this is the chapter 12 review part 2, and we are continuing question 10, where we have to do the Lewis structures of some formulas given here. And all the formulas for that question 10 are covalent compound because they are made of non-metals only or non-metals with metalloids. But here the examples are all made of non-metals only. Carbon and hydrogens are non-metals. So we'll do C2H4, and remember how I cannot format the subscript properly. So the 2 is a subscript for carbon and the 4 is a subscript for hydrogen. So let's look at the periodic table. So we have carbon and hydrogen in this compound, and carbon here in group 4A is a non-metal with 4 valence electrons. Hydrogen in group 1A, so it's an exception. Remember how even though it's in group 1A, it's not an alkali metal, it's a non-metal. But in group 1A means it has 1 valence electrons. So let's go back. So let's count the total number of valence electrons we will have to distribute. So we have 4 valence electrons times 2 carbon. So let's write it like this, plus 1 valence electron per hydrogen, and we have 4 hydrogens in the formula. So that's a total of 3 times 4, 12 electrons in total. So we have 12 electrons in total that we can distribute in this Lewis structure. So the second step is to position the atoms. And when you have covalent compounds like that, typically the molecules, because these are called molecules, you know that covalent compounds are also called a molecular compound. And they tend to be symmetrical. So you want to place the carbons, so let's place a carbon here. And then the other carbon will be bonded to the carbon, because hydrogens, remember how we said they need only a duet, which means 2 valence electrons around them, and they are satisfied by having just a single bond. And so because of that, the hydrogens will always be on the outside of your structure, never central atoms. So then the carbon will be bonded to each other, and then you will give 2 hydrogens to each carbon. So let's place one here on the left for that carbon, and then another one below, for example. And one to the right of this carbon, and below. So I gave 2 hydrogens to each carbon, right? This way it's symmetrical. And the 2 carbons will be bonded together. So let's distribute the single bonds between and attach all the atoms together. So we'll do 1 single bond between every hydrogen and one of the carbon. And then between the 2 carbons. So we've used 5 single bonds. So we need to count how many electrons we've used. From 12, we've taken 5 single bonds times 2 electrons. So times 5 single bonds times 2 electrons, that's 10. So we have 2 electrons left only at that point. Notice how all our hydrogens have their duets. You know, I can write that duets. Remember, duets is the name for 2 valence electrons, and that's what the hydrogen wants, because they like to gain just 1 more valence electron to be like helium, the noble gas that is the noble gas with atomic number 2, an exception among the noble gases. So I can already say that my hydrogens are satisfied. They each have their duets. So duets are done. But so those 2 electrons that are left, now we'll give them to the carbons. And so, for example, we could give two, a lone pair to one of the carbon. And this way we have used all our electrons. So 2 minus 2, we have 0 electrons left. This is important to count, how many electrons you have left. Because here you see that you can only satisfy one of the carbon. That carbon on the left has 6 valence electrons from the 3 single bonds, plus 2 more from the lone pair. So this one has an octet. But the other one, the other carbon has only 6 valence electrons around it from the 3 single bonds. So one of the carbon is satisfied, but not the other. So what will happen is that the lone pair here will have to be shared between the 2 carbons. So we will do a sharing, and normally I would have to redraw everything. So I cannot copy and paste the structure, but normally that's what you would do on paper. You want to show how you will share that lone pair. But here I cannot do it, so I will erase that lone pair from the first carbon and show how it's now a double bond between the 2 carbons. So now we have a double bond between the 2 carbons, and that will satisfy the octet rule for the both of them, because this double bond contains 4 electrons, right? 2 electrons per line. So that's 4 electrons that are shared, but they count for both of them. So 4, and then another single bond, that's 2 more electrons, plus the second single bond, that's 2 more, that's 8 valence electrons around each of those carbon. Of course, you count that separately, right? You count 1 carbon at a time, how many electrons it's surrounded by. So we have octets for both the carbons, right? Octet, octet. So when you want to verify that your Lewis structure is, that's what you want to do. You want to verify that each of the hydrogens has duets and each of the carbons here have an octet. And the second thing you want to verify is that the total number of valence electrons corresponds to what you should have, 12 electrons in total. So let's count and verify that this is correct. So we have 4 single bonds, and that's going to be 4 times 2, 8 valence electrons there, plus a double bond, 1 double bond. And a double bond is 4 electrons. So that's a total of, so 8 plus 4, 12 electrons total. And that's what we should have. So that's correct. So we have verified that our structure is correct. Let's move on to H3PO4. Again, the 3 is a subscript for hydrogen and the 4 is a subscript for oxygen. So this is called the phosphoric acid. And there's something you need to know about how to do the Lewis structure of acids. We know it's an acid because it has H as first in the formula, right? H is the first element in the formula, and we typically write acids formula with the hydrogen first to recognize them as acids. So this is still an ionic compound. It's made of only nonmetals. Hydrogen, phosphorus, and oxygen are nonmetals. So let's look at how many valence electrons they will bring each. So for this, we need to look at the periodic table. So we have hydrogen from group 1A will bring 1 valence electron. Then we have oxygen from group 6A, and so they will bring 6 valence electrons each. And then phosphorus in group 5A will bring 5 valence electrons. So notice how they are all nonmetals. So we know now 5 valence electrons for the phosphorus and 4 and 1 for the carbon and hydrogen. So let's count the total number of valence electrons. My text editor doesn't work. It's 1 valence electrons per hydrogen times 3 hydrogen plus 5 valence electrons from the phosphorus. So yeah, let me just say here first that it's from hydrogen. So plus 5 valence electrons from the phosphorus, and there is only 1. And 4 valence electrons, no, so it's not a carbon, it's oh, undo. So 6 valence electrons from the oxygen, and there is 4 of them. So let's count how many valence electrons. So that's 4 times 6, 24, plus 5 from the phosphorus, plus 3 from the hydrogens, and that's a total of 32 electrons. So how do we position the atoms? So what's particular about acids is that the hydrogens are bonded to oxygens. So each of these hydrogens will be bonded to one of the oxygens. So they are on the outside. And so P here will be the central atom. It's surrounded by 4 oxygens. So let's do that. Let's put P in the center and surrounded on 4 sides by oxygens. And then you will give 3 of the oxygen and a nitrogen, because there is only 3 hydrogens for, 4 oxygen. So 3 of them will have, so let me write the hydrogen here for that right oxygen, and then the other one here for that left oxygen. So now I am ready to place the single bonds and connect each of the atoms together. So phosphorus will be bonded to each of the oxygen. So 4 single bonds between phosphorus and the oxygen. Then, as I told you, the hydrogens are bonded to the oxygen. And because there is only 3 hydrogens, one of the oxygen doesn't have a hydrogen bonded to it. So let's count how many electrons we've used from there. So 32 electrons we started with, minus, so we placed 1, 2, 3, 4, 5, 6, 7 bonds. So 7 bonds times 2 electrons each. So that's 14. So 32 minus 14, that's 18 electrons left. So we still have 18 electrons to distribute. And now we are ready to do the lone pairs to complete the octet of the outside atoms first. So remember how hydrogen wants a duet. So if we write here duet, do we have duets already? Yes, we do, right? If you select here the, okay, these hydrogens, they have their duet. So the duets are done. Now we need to do the octets on the oxygens. And so let's start with the oxygens that are bonded to the hydrogen. So we will give, so they already have 2 single bonds bonded to them, right? They are bonded to P and then bonded to H. So that's 4 electrons around them already. So they only need 2 lone pairs. And I will put 1 lone pair on that side and the other lone pair on the other side here. So by giving them 2 lone pair here, plus the 2 single bonds, that's 8 valence electrons around these oxygen that are bonded to the hydrogen. So we can do that to all 3 of them because they are similar. And let's count how many electrons we've used. We've used 2, 4, 6, 8, 10, and 12. We still have room to, so 12, minus 18 means we still can give those 6 valence electrons left over to the other oxygen here that is by itself, single bonded to P. So it has only 2 valence electrons around it. So we can give it 3 lone pairs, 6 more electrons so that it gets an octet. So let's count. We had 18 electrons left over, and we've used 6 valence electrons in that last oxygen, plus 4, that's 10, plus another 4, 14, plus another 4, 18. So we've used all electrons at that point. 0 electrons left. That means we cannot bring more electrons to the structure. Everything is there. So let's see if we have our octets. So let's write octets here. You want to verify that all your atoms that are not hydrogens have an octet. So let's see. These oxygens, they have an octet because 2 single bonds, that's 4 electrons, plus 2 lone pairs, that's another 4 electrons. So they do have an octet. All 3 of these. And then this 4th oxygen has 6 valence electrons from the lone pairs, plus 2 from the single bond, that's 8 valence electrons as well. So all oxygens have their octet. Now P in the center here has 4 single bonds, and that's 4 times 2, 8 electrons around it. So it does have an octet as well. So we can say all atoms have their octet. So that's good. We have distributed all electrons. So let's verify now that we do have the correct number of electrons in that structure. So we have, we said 1, 2, 3, 4, 5, 6, 7. Oh, let's write this differently. So 7 single bonds. So 7 single bonds times 2 electrons each, that's 14 electrons from the single bonds. Plus we have, so I will count lone pairs. So 1, 2 on one oxygen, 3, 4 on another, 5, 6, 7, 8, 9. So we have 9 lone pairs. Lone pairs of electrons, because it's pairs, so it's times 2 electrons each. So that's 2 times 9, 18 electrons from the lone pairs. So is 14 plus 18, that's 32, and that's exactly, 32. 32 electrons. And so that confirms that we have the correct total number of valence electrons in that structure. So that shows that this structure is the correct structure for the phosphoric acid. So P2H4, again, the 2 should be a subscript for P and the 4 is a subscript for H. So we have 2 phosphorus, 4 hydrogens. We already know how many valence electrons they each have because we did H3PO4. So let's count the electrons here. So we have 5 electrons from the phosphorus, and there is 2 of them. So that's the phosphorus. Plus 1 electron per hydrogen, and there is 4 hydrogens. So 2 times 5 is 10, plus 4 is 14 electrons in total. Okay, so that's the number of electrons we need to distribute. So we'll do the position the atoms now. So we have 2 P's, 4 hydrogens. So as always try to make it symmetrical. And so here, again, because the hydrogens wants a single bond only, you know, to have duets, they will be on the outside. So you want to place the 2 phosphorus together in the middle and they will be bonded together. And then because there is 4 hydrogens, so you will give the phosphorus each 2 hydrogen, very much like the structure above with the carbon. So that's how you want to place them. And then you do the single bonds. So 1 single bond between every hydrogen and one of the P. And then bond the phosphorus together. So how many electrons did we use by doing this? So we started with 14. So let's count here, 14 minus, we used 1, 2, 3, 4, 5 single bonds. So 5 single bonds times 2 electrons each. That's 10. So we have 4 electrons left. So notice how we already have our duets, right? I can write, let's see, I will write duets here. So we do have our duets because each hydrogen has a single bond. So they are all already set. So we have our duets. And what about octets? So let's write octets. So the phosphorus, they want octets, right? They are regular atoms. And right now, so if you look at one phosphorus at a time, so let's look at the left phosphorus, it's surrounded by 3 single bonds. So that means it has 3 times 2, 6 electrons around it. And if you look at the other phosphorus, it's the same, 3 single bonds times 2, it's 6 electrons. So they don't have their octet yet. So those 4 valence electrons left will be distributed to the phosphorus. And so because they already have 6 valence electrons, so you want to give them a lone pair each. And this way that will bring their number of valence electrons from 6 to 8 for each of them. And this way we are using all electrons because 4 minus 4 is 0 electrons left to distribute. And so this way, the phosphorus, they have their octet, right? We can see that 6 valence electrons from the 3 single bonds plus the lone pair, that's 8 for each of them. So that looks like it's finished. So let's verify that we do have 14 electrons in total. So we have 1, 2, 3, 4, 5. So 5 single bonds. Single bonds. 5 single bonds times 2 electrons each, that's 10 electrons. Plus, we have 2 lone pairs. 2 lone pairs. Two lone pairs times 2 electrons each, that's 4 electrons. And that's it. So, and that's 14. 10 plus 4 is 14. So we do have our 14 electrons in total, which is the correct total. So that means, the total is correct. And so we both have the correct total and octets and duets completed. So that's the correct structure for P2H4. So we'll move on now to HCO3 negative 1. So HCO3 negative 1 is called the hydrogen carbonate or the bicarbonate. That's polyatomic ion. So we will do HCO3 here in the right corner. And so we see that it's made of non-metals only. Hydrogen, carbon, and oxygen. And we already know what is the number of valence electrons that each brings. So hydrogen brings 1 valence electron, and there is only 1. So not times. So 1 from the hydrogen. Plus we have carbon. Carbons are in group 4A, so they bring 4 valence electrons, and there is only 1. Plus oxygens. Oxygens are in group 6A, so they bring 6 valence electrons. And there is 3 oxygen in this structure, so times 3, that's for the oxygen. So 3 times 6 is 18, 19 with the 1 from hydrogen, plus 3 is 23. Oh, and I forgot something. I forgot that there is the negative charge, right? And that's what you should not forget when you are doing polyatomic ions. This negative charge means there is an electron in excess that is not cancelled out by a proton. So you need to add that. So plus 1 more from that negative charge, okay? And so that brings the total to, so 18 plus 2, 20, 24. 24 electrons in that structure in total, okay? So that's the total number of valence electrons we have to distribute. Okay, so second step, you position the atoms, that hydrogen carbonate or bicarbonate ion. This hydrogen, again, is first in the formula, and that indicates that the hydrogen will be bonded to an oxygen. It's, if you will, it's an acidic hydrogen. So in, acids, the hydrogens are typically bonded to the oxygens when there is an oxygen in that formula. So that means you want to give the hydrogen to the oxygen. And then the carbon will be the central atom. So let's place the carbon in the center. Surrounded with 3 of the oxygen. Carbon is always a central atom, never put it on the outside. 3 of the oxygen, and then you will give 1 of the oxygen a nitrogen. So let's place it here, for example. Okay, it doesn't matter which one, right? So give 1 of the oxygen, the hydrogen. Next, you do the single bonds. So carbon is bonded to the 3 oxygens, and then the hydrogen is bonded to 1 of the oxygen. So this way we've used 1, 2, 3, 4 single bonds. So from 24 electrons, we've used 4 single bonds times 2 electrons each. 2 times 4 is 8. So 24 minus 8 is 16. So we have 16 electrons left. So remember how total was for the upper number there. So we still have 16 electrons to distribute. And let's just say, let's write this somewhere here, that let's write duet, because that hydrogen wants a duet. And you can see that the hydrogen already has its duet. So it's happy here. We don't need to worry about the hydrogen. So then we want to continue give the electrons to the outside atom as lone pairs. And so the outside atom are the oxygens. And so let's start with the oxygen that has already 2 single bonds. 2 single bonds means 4 electrons around it. So it needs 4 more to get 8. So you will give it 2 lone pairs. 1, 2, and 2 lone pairs, that means 4 electrons. So that satisfies that oxygen. The other oxygen, they have only a single bond, so they need 6 electrons more. So by giving them 3 lone pairs, we get 6 around them, plus 2 with the single bond, that's 8. And so that will satisfy that oxygen. And this one is the same. It needs 6 around it. 6 from 3 lone pairs plus a single bond, that's going to be 8 valence electrons. So let's count. We've used 6 on one oxygen plus 6 on another, that's 12, plus 4, that's 16. So we already have used all our electrons here. So 16 minus 16 is 0 electrons left. So we have 0 electron left to distribute. So do we have our octet? Let's write this somewhere, octets. So the oxygen and the carbon, they want octets, right? So we've made sure that this oxygen has an octet with 3 lone pairs plus a single bond, that's an octet. Here, 3 lone pairs plus a single bond, that's an octet. And here, 2 single bonds plus 2 lone pairs, that's an octet. However, carbon doesn't have an octet. It has 3 single bonds, which means only 6 valence electrons around it. But we have no more electrons to distribute. So that means we cannot, bring more electrons into the structure. We have used everything that was available. So one of the oxygen has to share a lone pair with the carbon. And here it is important which one you're choosing here. It cannot be the oxygen that has already 2 single bonds, because, there are common patterns for, hydrogen, carbon, oxygen, nitrogen, etc. And carbon likes to make four bonds, for example, 4 single bonds, or a double bond and 2 single bonds, or two double bonds, etc. But the oxygen, it's common. It commonly wants only 2 single bonds. And so you cannot make it a double bond with that oxygen that is already bonded to the hydrogen. That's important here to not do that. So you want the lone pair to come from one of the other oxygen. And so if I show it here, let's take it from this one, for example. So it will have to come from that oxygen or the other one. They are similar, these two. So it can be one or the other. So let me, ideally you want to rewrite everything. So let's rewrite everything. So I've redrawn the structure below, and what changes is that the oxygen below will lose one of the lone pair, and it will become a double bond with the carbon. So that oxygen is sharing its lone pair with the carbon. And so that gives the carbon an octet, which is what we wanted, because if you look here now, carbon is surrounded by 2 single bonds, that's 4 electrons, plus a double bond. And in a double bond, there is another 4 electrons. So 4 plus 4, 8. So we have an octet around that carbon now. And if we check the others. This still has an octet, and this oxygen still has its octet because 2 lone pairs, that's 4 electrons, plus the double bond, that's another 4 electrons. So it still has its octet. That oxygen with its 2 single bonds and 2 double bonds also has its octet. And then the hydrogen had its duet. So we can see that they all have their octets or duets. So the second thing you want to verify is that the total number of electrons is the correct one. So in the structure you have. So let's verify this. And so we have 3 single bonds. Let me write this in darker color. So 3 single bonds. So 3 single bonds, that corresponds to 3 times 2, 6 electrons, plus a double bond, 1 double bond, double bond. 1 double bond is 4 electrons, right? Because that corresponds to 4 electrons shared. And then we have how many lone pairs? 1, 2, 3, 4, 5, 6, 7. 7 lone pairs. Seven lone pairs times 2 electrons each, that's 14. 14, so 14 plus another 4, that's 18, plus 6, that's 24. So we do have the correct total. So the total is correct, and that's good to check this. So this is the correct structure. There is only one thing missing here. It's an ion, right? It's an ion, so you need to show that it's an ion, and you need to show the charge. And for this, we use brackets around the structure. So you need brackets around that structure, and then you need to show the charge on the upper right corner. And let me put it in color so we see it here. Right, the negative sign here is for the negative sign of the hydrogen bicarbonate ion. And so that now it is complete. You need the brackets with the charge in the upper right corner.